Hello, and welcome to Taylor's Classical Mechanics. This is going to be a solution to problem 4.28 in the book. So I'm going to read through the problem statement. So it says that we're going to have, consider a mass M on the end of a spring. The spring will have a force constant of K. And it's going to be constrained, the mass is constrained to move on the horizontal x-axis. Now, we're going to start off with the spring in its sort of rest length position. So we're going to make our origin wherever the mass is at the start. So the center of mass of our little block, we're going to make that the origin. And, the spring is extended maybe to the left. You can kind of think of it, it's attached to the wall or something on the left. And we're just going to find our origin, our zero position for the mass, as whatever that rest length is. But we're defining our origin at the mass so that we can just say that the mass's position is zero at the start. And then if we pull the mass or push the mass, the displacement from the equilibrium will just be the value of x it is, because the final position minus the initial position, if the initial position is zero, the origin, then the rest length, or the difference in length between the rest length and the current length is just the value of x, if that makes sense. So that's how we're going to define our coordinate system. And of course we know that the potential energy of a spring system like this is 1/2 kx squared. And it says at time t0, the mass is sitting at the origin, and then we give it a sudden kick to the right so that it moves out to some maximum displacement, x max equal to a. So a is going to be whatever we, have pulled the mass out to the right of the origin. And then, it's going to be let go, and then it's just going to oscillate back and forth. There's no friction or anything. It wants us to write down the equation for conservation of energy and use this to solve for the mass's velocity, x dot, in terms of the position x and the total energy, E. And then part B wants us to show that the energy is equal to 1/2 Ka squared, and use this to eliminate the energy from our expression for the velocity. And then it wants us to use this expression that we derived in chapter 4 for t, which will give us the time t that we reach some velocity. So we're basically solving for t in terms of the velocity x here. And then we're going to use this to solve for the position of x in terms of t. That's what part C is all about. So let's go ahead and get started. So I apologize if I sound a little sick. It's just I have some congestion going on, but I feel okay. So I'm going to try my best here. So the total energy of the system, right, is the kinetic plus the potential. And in this case, the kinetic is going to be 1/2 mv squared. Should not be v dot. Really, this should be v or x dot. I'm going to make this x dot. X dot squared. X dot meaning the derivative of the position. So this is really the velocity. So 1/2 mv squared plus 1/2 kx squared, which is the potential energy. Right? At any given point in time, this is the generic kind of total energy of the system. Now we can solve for the velocity x dot by, of course, subtracting over 1/2 kx squared. So we have 1/2 mx dot squared is equal to E minus 1/2 kx squared. And then we can multiply over 2 over m. And then we can take the square root of that to basically give us that the velocity as a function of position is the square root of 2 over m times the square root of E minus 1/2 kx squared. And this is part A. Essentially, this is what we wanted to derive for part A, is the velocity of the mass as a function of the position. So that tells us based on where the mass is, how fast is the mass moving. Now, for part B, when the mass is at its maximum length, it's reached the maximum length that it's going to reach, it should have no kinetic energy left, right? It should be basically at a standstill because it's about to start oscillating back in the other direction. So at the maximum length, which we define as A, the problem says x max is A, the kinetic energy T is 0. And if T is 0, then the total energy of the system at the maximum length position is just it's all potential energy, right? It's about to convert back into a kinetic energy, but it's all potential. So it's gonna be 1/2 k A squared, where you plug in A for the x squared in the potential function. And then we can plug this expression for E back into our expression for the velocity to kind of get rid of the E in our velocity function. So just doing that, we have the square root of 2 over m stays the same. Then we have 1/2 k A squared minus 1/2 k x squared inside of the square root here. Now, if we factor out the 1/2, then we'll have out of this, we can factor out the 1/2 from both these terms, and that's going to be the square root of 1/2, or, the square root of 1, which is 1, and then the square root. So it's going to be like basically 1 over the square root of 2. That 1 over square root of 2 can cancel out this square root of 2 on top here. So that will go away. And there's a k here, so we can factor out the square root of k, and we can rewrite all these constant terms as just the square root of k over m. And so that's what we do here. We factor out the square root of 1/2, and that's going to cancel the 2 here. And then we factor out the k, and we group that with the square root of m, so we get the square root of k over m. And then what's left inside of this square root is just a squared minus x squared. And then we can rewrite this as just x dot of x is equal to omega times the square root of a squared minus x squared, where we're just using the variable omega to represent the square root of k over m. And if you've studied simple harmonic motion, this should look familiar because this omega term ends up being the frequency of oscillation of the system, which is kind of why I write it as omega suggestively. So this square root of k over m ends up being the frequency of the system, and we can rewrite our velocity like this. So we've gotten rid of the e from our equation here. And then don't mind this at the bottom. That was some stuff I scribbled out. But now we can use this expression for t. So we can solve for t by using the velocity function x dot. So t, this is derived in the textbook in chapter 4. So if you don't know how this equation was derived, you can go back to the section of that and run through that. But we can plug in our function for our velocity here and solve this integral, and that should give us t in terms of x, essentially, in terms of position. So plugging in x dot here, we have 1 over omega, right? We had omega, but then we're plugging in not x dot, we're plugging in 1 over x dot. And then on the bottom, we have 1 over a squared minus x prime squared. I'm using prime notation here because our variable of integration is going to go from 0 to x. So I'm using x prime as the integration variable. And this integral is pretty simple. I mean, it ends up being like a standard integral. So I don't go through like really solving it, but you can get it into the form of a standard integral and then just kind of go from there. So if you use the substitution u equals x prime over a, then du with respect to x is just 1 over a dx prime. And then we can use this substitution to plug into here. So a du is dx is dx is a du, or dx prime, I mean, is a du. And then we can plug in our expression x prime is u times a, so we can plug that in here. So what we get on the bottom is the square root of a squared minus a squared u squared, because x prime squared is u squared a squared. Then we can factor out the a squared from the square root, and that'll just be the square root of a squared, which is a. So the a's end up canceling, and we're left with just 1 over the square root of 1 minus u squared, since we factored out the a there. And this form of the integral, 1 over the square root of 1 minus our variable of integration squared, this is just a standard integral for the arcsine function. So I kind of just do that. If you really want to like solve this integral properly, feel free, but I just went ahead and like recognize that this is just a standard integral and kind of went with that for now. So the t as a function of position ends up being 1 over omega times the arcsine of x over a, because this integral is the arcsine of u, but u is x over a, so we plug that back in. And this is the answer to part B as well. So this is our, given some position x, we know when we'll get to that position. T tells us when we'll get to that position. And then part C is just rearranging or resolving this, so we get the position as a function of time, which is generally more useful. So of course we can multiply omega over, and then we get arcsine of x over a equals omega t. We can then take the sine of the arcsine, which ends up negating the arcsine because they're inverses of each other. So we get x over a equals sine of omega t, because we've got to take the sine on both sides. Then we multiply the a over, and we get that the position as a function of time is just a sine of omega t, which should look familiar to you if you've studied simple harmonic motion. So this is telling us that the position of the mass ends up being an oscillating function, or just being simple harmonic motion. And then, this means that, the position ends up repeating itself every 2 pi. So that means when omega t is equal to 2 pi, that's when it repeats. And so that means every time that t is equal to 2 pi over omega, where omega, remember, is the square root of k over m. So whenever t is equal to 2 pi times the square root of m over k, because it's 1 over omega, then this is when the frequency of oscillation, essentially. So when t is 2 pi times the square root of m over k, which are constants that we would know. We know the mass and we know the spring constant. So we could figure out at what time, like how long the time interval is that it takes, for it to go through one period. And that's it. So that's problem 4.28. If you guys have any questions, feel free to leave them in the comments below. I'd be more than happy to answer anything, or if something was unclear, just let me know. So thank you guys for watching, and I will see you guys later.